So in today's lesson, we're going to discuss about trigonometric identities and what to do with them. So the first things first, let's start off with what is a identity. So an identity is a mathematical expression where it looks different, but it is the same thing as another mathematical expression which looks different. For example, we have an expression that looks like this, but we know that when you expand this, you end up getting 2x plus 6. So they look different. One is in factored form, one is in expanded form, but they're actually identical. They are the same. Or when we talk a bit about adding, subtracting numbers, we have 2 plus 3. Well, we know that 2 plus 3 can be written as 1 plus 4. They look different. The numerical expression on the left side and the right side looks different, but they end up with the same result because they both equal to 5. So when it comes to trig identities, what that means is there's several trig identities where they look different, but they're actually the same. So let's start talking about this. We talked about this in the past videos, reciprocals. So cosecant is related to sine. However, cosecant is the reciprocal of sine theta. Secant, the reciprocal of cosine, and cotant is the reciprocal of tan. So these statements on the left side and the right side, they look different, but they're actually the same. Just to expand a bit about the reciprocal identities, so if you notice, sine is opposite over hypotenuse, but cosecant is hypotenuse over opposite, so they are reciprocals of each other. So we cannot say that sine theta is equal to cosecant theta because the O is on top, whereas the O is the bottom. We cannot say this statement is not true. So the question right now is, if I had cosecant, which is H over O, how is it that what I can do with this to make it the same orientation as this? So what I'm going to have to do is I'm going to have to flip these. And so when I flip them, I'm actually taking the reciprocal, which becomes 1 over H over O over H, or 1 over sine theta. The other way works too. For example, I can say that sine theta is the flip or the reciprocal of 1 over cosecant. So in other words, what I'm trying to say right now is that each of these statements can be rewritten in a different format. So in other words, I can say that cosecant, so cosine is the same thing as 1 over secant theta, or tan theta is equals to 1 over cotan theta. They are reciprocal relationships between each other, depending on which one you start off with first. So in this slide here, we're going to talk about the difference between an identity versus an equation. Because some students, when they see x on both sides, they assume that they're going to solve for x. So solving for an equation is different than establishing what an identity is. So let me just explain the difference. So let's have a look at this one here, over here. So we know that you can get from here to here, they are both equivalent. One's expanded form, one's factored form. So based on these two statements, if I were to separate them, what that means is, let's just say I want x to be 4. If I sub in 4 into here, 4 plus 3 versus 2 times 4 plus 6, I end up getting exactly the same number, 2 times 7, 14. This is 8 plus 6, which is 14. So what this means is, whatever number that I put into x, it could be 4, it could be 5, it could be negative 100, I'm going to end up getting a number that's the same. So if I were to try to put in, let's just say x is 100, all right? So you would have 100 plus 3, you have 2 times 100 plus 6, I get up 206, I get 2 times 103, which is 206. So basically what that means is this statement is always true for all the x values that we sub in. In other words, I'm not actually finding x or solving for x, because the reason why is x works for every single thing for these two statements. So if you're to solve, let's just say you mistaken this question for solving. So you have 2x plus 3 is equals to 2x plus 6. And let's just say you solved it. 2x plus 6, 2x plus 6. You bring the 2x over, minus 2x. You have 6, bring the 6 over. That becomes 0x is equals to 0. So this equation here actually says a lot of things. It actually means that, well, 0 times what will give you 0? Well, 0 times anything. What this means is x is anything, meaning XER in this specific example. So what that means is x could be anything. So if x could be anything, that means that these two equations are exactly the same. Or if you do think of this as think of this graphically. So imagine mx plus b. This is a straight line with a slope of 2 and 6. Looks like this. Well, what does this line look like? Well, this line is exactly the same thing, so they're pretty much overlapping each other. So the question is, when will they cross each other? They always cross because they are identical. Identical. So when something is identical, we don't really need to solve it because we kind of know the answer already, meaning, well, they're on top of each other, these two graphs, so that means they're always crossing each other. So let's turn to the trig identity and how it's related to the other slide. So here's the statement, reciprocal identity. The statement is true. So what that means is whatever number that you put in here, for example, let's put in 30 degrees or 45 degrees or 100 degrees. So if you sub in 100 degrees into each side and do some calculator work, you're going to get the same number. Or let's just say instead of 100 degrees, you sub in, for example, 5 degrees or 8 degrees or 10 degrees. You're going to get a real number that's going to end up being the same from the left side and from the right side. So in other words, theta could be whatever number that you want. So I'm going to put here, theta could be ER, as long as the angle that you put into each of the left-hand side will give you an actual real number. So now I don't want to get into it, but there are some restrictions to this. I'm going to put here, there are restrictions for these specific reciprocals because you got a variable in the denominator. So it can't be ER, but it has to be a specific, there are specific restrictions, which I'm not going to get into yet. So the next identity is called quotient identity. And for those that watched the previous videos, I did mention about this identity. So we'll just start from scratch. So imagine you have a unit circle and you have a point, and this point we'll call X and Y. And this circle, it doesn't have to be unit. We'll just open it up and call it a circle with a specific radius. And this is your principal angle. And based on what we know that the X is related to cos and the y is related to sine. In other words, I'll put here y and I'm going to put here x. And if we're to use trigonometric ratios to solve for this, what that means is if I want to solve for x, we know that this is adjacent and this is your hypotenuse. So in other words, cos theta is equals to x over r, whereas the opposite here, OPP, versus the hypotenuse, we'll use sine theta is equals to y over r. And I'm just going to isolate x. So x is equals to r cos theta and y is equals to r sine theta. So that's what that is. Well, the question right now is, I've talked about cos, I've talked about sine. Well, what about the other trig ratio, tan? Well, we know that tan theta, so remember what tan is? Tan is opposite over adjacent. Now, in this case, this is my opposite and this is my adjacent. So it's the same thing as y over x. That's correct. And look at the one above over here. What is actually y? Y is r sine theta. And what's x? X is r cos theta. In other words, if I were to simplify the radius, I end up getting sine theta over cos theta. So this here is a trig identity. It's called the quotient identity. The reason why it's called a quotient because quotient is related to division. So tan is the same thing as sine divided by cos. And let's talk a bit about the reciprocal of tan, which is cotant. So cotant is what? So cotant is not opposite over adjacent. It is the other way around, adjacent over opposite. So which is the x over the y. So things are flipped. In other words, x is going to be r cos theta. I'm just showing all the steps. R sine theta, we do the same thing. The r's are reduced, and I end up getting at the end cotant theta is equals to cos theta over sine theta. In other words, these two are reciprocals of each other. You can actually see in the blue that tan is sine over cos, and therefore cotant is the flip of tan, or cos over sine. So the last identity is called Pythagorean identity. So all I did was I just wrote down the stuff from before from the previous slide. Now, what is Pythagorean identity? Well, Pythagorean identity is related to Pythagorean theorem. Back in grade 9 or 8, you learn how to solve the sides of a right-angled triangle based on what's given. So here, if you notice here, I'll use red. So red, we have a right-angled triangle, and we know all the sides of these. That's x, that's y, and that's the radius, or r, hypotenuse. And what that means is based on Pythagorean theorem, x squared plus y squared is equals to r squared. Remember that this comes from a squared plus b squared is equals to c squared, where c squared is the longest side of the right angle triangle. In other words, so this is what we have. Now, what is actually x? Well, x is actually, remember what from the previous slide, x is the same thing as r cos theta. So all I'm going to do is replace all the x's with r cos theta in brackets. I'll put a square because a square is over there. So what's y? Well, y is r sine theta is equals to r squared. And all I'm going to do right now is expand. So remember, power rule, everything gets squared. Everything gets squared. So I'm going to put here r squared. I'll put here cos theta in brackets square plus r squared sine theta bracket square is equals to r squared. And if you notice here, we have r's everywhere. So what I'm going to do is I'm going to divide everything by r squared. Or if you wanted to, you can factor the r squared from the left-hand side. R squared, bracket, leaving the cos square plus sine square, which equals to r squared. So over here next, because this is in factored form, I can divide both sides by r squared. If I divide by r squared, what happens? Oh, I get a 1, so I'm not going to put that down. I end up getting cos theta squared plus sine theta squared is equals to 1. This here is called the Pythagorean identity. So in terms of format-wise, this is fine, but we like to not have so many brackets. In other words, I can take the square and rewrite it this way. So that little square can go before the angle, and it means the same thing, so they're the same thing. We just don't want to have so many brackets. So over here, we have, this thing I'm circling is my Pythagorean identity. I prefer to have the sign first. It doesn't really matter, but it's a personal preference. So what this means is, remember what identity means? It means that whatever number that you put into the angle, you're going to get, in this case, you always get a 1. So what that means is if I take sine theta and put 5 degrees plus cos 5 degrees. If I put this in my calculator, I will always get a 1. So I'm going to have to bother putting these two numbers in my calculator because I know that this statement is true because we actually proved it from up here. That is going to be equal to 1. So the Pythagorean identity has different forms or different variations. So let's talk a bit about 2 plus 3 is equals to 5. So 2 plus 3 is equals to 5. So this is a identity because the statement is true. Left side, right side, they look different, but they're the same. Or I can rearrange this. So if I say that, oh, 2 is equals to 5 minus 3, I just took the 3 and brought it over. So I sort of like reformatted this. This statement is also still true. Or I can say that, let's bring 2 minus 5 is equals to negative 3. So what I did was I actually brought the 5 over, subtracted 5 from both sides, and subtracted 3 from both sides. So even though it looks different, but this statement, left side, right side, it is still true. So all of these three things are considered the same identity, but it's just reformatted. So in other words, what I'm trying to say is, going back to the Pythagorean identity, so if I were to take, okay, I'm going to take, for example, the cosine square and bring it over to the right-hand side, that becomes a negative. This is also an identity. It comes from the Pythagorean identity. So I'm trying to do different variations, or maybe instead of bringing the cosine over, bring the sine over. In other words, cosine. So I'm going to leave the sine and cosine on the left-hand side. I'm going to bring the cos to the other side, or subtract sine square on both sides, 1 minus sine square theta. So these statements, even though they look different from the original one that we had, but we're just sort of reformatting it. It is still considered a Pythagorean identity, just in a different format. So if we have a statement that's true, 2 plus 4 is equals to 6, so what that means is this statement is true. So if I do something to the left-hand side and do the same thing with the right-hand side, the statement is also still true. So what I mean by this is if I take both sides and I doubled it. So if I double 2, that becomes a 4. I double 4 becomes an 8. I double 6 becomes a 12. Now, is the statement true? It is still true because 4 plus 8 is equals to 12. Or I don't have to double it. I can sort of divide it by 2. Let's divide everything by 2. So half of 2 is 1. Half of 4 is 2. and half of 6 is 3. Is 1 plus 2 equals to 3? Yes, the statement is still true. So what I'm trying to say is, if the statement is true like this, and if you treat both sides the same, whether you add something on both sides, subtracting on both sides, or you multiply something on both sides, or you divide something on both sides, the statement will still be true. It looks different, but the statement is still true. So let's take the Pythagorean identity and do something to both sides. So what I'm going to do right now is I'm going to divide everything by the same term. In this case, I'm going to divide both sides by sine square. And what that gives me is, I'll put in red, I'll show you divided by sine squared, divided by sine squared, divided by sine squared. And what does that become? Well, let's simplify this. Sine divided by sine will give you 1 plus. Now, cos over sine, there's 2 of them. So this actually means there's actually 2 coses and 2 sines on the bottom. So I'm just splitting it up for you guys. This is the same thing as sine, and then I'll put here times 1 over sine. I'm trying to show you that I'm breaking into 2 parts. Now 1 plus. Now this was from the previous slide. Cos over sine is a quotient identity. That means it is the quotient. That means it becomes cotant. And there's 2 of them, so I'll put them side by side. And this is the same thing as, well, this is the reciprocal identity. That becomes cosecant, and there's 2 of them right next to each other, cosecant. I'm just going to simplify this, and we end up getting this. So cot becomes cot square. So remember how I mentioned that there's a different format? You can rewrite this out as a little 2 before the theta, and this is the same thing as cosecant square. So this here is another format of the Pythagorean identity. So the next one I'm going to do is I'm going to divide both sides by cos square. So over here I'll use blue, divide everything by cos square because I'm treating both sides the same of this identity. And I'm getting, so this one here, I'm not going to show you all the micro steps, but sine over cos is a quotient identity. That becomes tan, but we got 2 of them, plus cos divided by cos square gives you 1. And 1 over cos square is the same thing as the reciprocal identity, which is the same thing as secant square. So this one here is also considered a reformatted version of the Pythagorean identity. So here we have a summary of all the trig identities. So left is the Pythagorean identity. So here was the original one that we proved using the circle with a specific radius. And these ones are the variations, the ones that I reformatted. The middle one here, as I mentioned, tan and cotant, the quotients of sine and cos, depending on which way that you want it, and then the reciprocals.